Okay, folks, we are going to be talking about the lecture number 5 today, which is the lecture on measures of dispersion. Now, measures of dispersions are used to be able to identify how the data in the sample would spread around its central value, which in our case, we're going to use all of our measure of dispersion to be with the central value in the whole idea to be the mean of the sample or the mean of the population when we talk about the dispersion of the population. Okay, so we already have one measure of dispersion. We had introduced that time ago. We call that measure of dispersion range. So the range as a measure of dispersion is the difference between the biggest and the smallest value in the sample. So if you're talking about a sample, if you're talking about population, it's the same thing. So if you have a sample like this, for example, 1, 2, 5, 7, 8, the difference between the smallest and the biggest is 7, so that would be the range. But then again, if you have a sample 1, 1, 1, 1, 8, the range would again be 7. If you have a sample 1, 8, 8, 8, 8, again, the measure of this measure, the range would be 7. So that's not good enough because apparently the samples are quite different. Those two samples are quite different. So we need to have something better. And now we could consider a measure of dispersion of a sample like this to be what is the average distance of the sample points 1, 2, 5, 7, and 8 from the mean. So I need to know what the mean is. That's not hard to calculate. The mean x bar is 1 plus 2 plus 5 plus 7 plus 8, 23, divided with 5 of them is 4.6. Okay, so I have that. Now, what happens here, I'm going to use 1 here, and I'm going to have 2, 3, 4, 5, 6, 7, 8. Okay, try to make some proportion. The 4.6 is about here. Okay. So if I'm thinking about where are these points, the sample points, these, they're kind of away from the mean. Now, this one is, the 2 is 2.6 away from the mean. You just have to subtract this one and this one to find the difference. This one is one further, so it's this guy. 3.6 away. This one here is not that much away from 4.6. It's only 0.4. 5 minus 4.6 is 0.4. So, okay, but then these two are further. This one is 2.4, and the 8 is 3.4 away. Okay? So now, the deviation that would be, the idea of deviation would be that I'm looking for something average here. What's the average, the distance away from the central point? So these guys are going far away. This one is very close. This one goes further. This one goes further. What's the average of that? So that is what we call absolute deviation. And that would be the average of these distances. 3.6 plus 2.6 plus 0.4 plus 2.4 plus 3.4, all of that divided now with 5, because there are 5 of them, right? So that would be the average, and that will turn out to be 6.2, 6.6, 11.6, 12.4 divided with 5. Okay, this is not too hard to do. Looks like a 2 times into 10, and then you have 24, this is 0.48. Okay, so that's the average distance. Okay, so this one is kind of quite closer to than this. This one is about a little more than that. This one is a lot more than that. This one is almost like this, and this one is further than this. So, but on average, they are 2.48 away from the mean. Okay? This is one of the possible measures that we could use. We could use absolute deviation, which is the average jump away from the mean of the sample. Data points are not the same as mean. They go away, right? They're not on average. On average, they mean, but themselves are different. Some of them are going further, some of them are going, some of them are quite close. So there is this difference that makes this person interesting to us, because they're not all the same. Okay, so for some interesting theoretical reasons, which we are not going to be explaining in this class, the absolute deviation is not something we're going to use. We could, but we're not going to use. The most of our calculation will require, in the future, there are theoretical reasons for that, to calculate something called standard deviation. Standard deviation, not an absolute deviation. Okay. Standard deviation has two formulas that we use. It will depend whether we're going to use the standard deviation of the sample, which we call sample standard deviation, or we're going to use a standard deviation of the population, in which case we call it population standard deviation. They're not the same. Now this is very important to make that distinction right from the get-go, which means that you need to know when you're dealing with the set of numbers whether that is a sample or a population. Now in this case, I'm going to talk about this as a sample. And then we have this formula that has the same idea. It has the same idea of calculating average displacement away from the mean. This formula. What you're doing here, it looks very sophisticated, some big calculation, but it isn't. This is the same formula I wrote here on the board, and I put the numerator of that fraction over there in some sort of a cloud, because I'm going to show you a better way to calculate it. The idea here is that I have to find the mean, which I already have. It's 4.6 in this case of the sample I have on the board. Then I have to subtract every data point from the mean. I already did that. I got 3.6, 2.6, 0.4, 2.4, 3.4. Then I have to square that. Now that's a new thing here. I wasn't doing that before. So I have to square that. And once I square that, so I have a 5 now displacements that I squared. Now I have to total that. I have to sum it. So this sigma, this Greek S, this is Greek uppercase S that looks like an inverted E. That is actually a symbol for a sum. So I need to sum those 5. This is the thing that I was doing, that, well, I was calculating absolute deviation as well. So I need to sum it. And then I need to average that. I need to average that with this n minus 1. This is not n, not 5. This is 4. N is the size of the sample, so that would be 5. But actually you're averaging with 4. This is called degrees of freedom. So sample size 5 has 4 degrees of freedom. That's interesting. Now, population does not have a degree of freedom. Population is 1 only. You can't have 2 populations. I mean, for the same variable. But you have multiple samples, so the population will not have this. In population, we will average with the size of the population. But when we are doing the sample, we are averaging with the degrees of freedom of the sample. Not 5, but 4 in this case of the sample. And once you're done with that, you take a radical. So it's quite a lot of calculation, right? A radical actually basically just reverse the impact of the square we were doing on the way we were squaring. So on the radical, just reverse this impact. So the idea is still the same. We need to, this is going to be approximately what on average the data points are going away from the sample. What is the average displacement from the mean of the sample. So let me show you how this formula is used. First of all, you have here this numerator that I put there in the cloud over there. So the this piece here on the in the fraction here. So if I'm going to calculate this numerator, I will need to get the difference, the square, the total. Okay. I can also calculate that by using this formula here. This is just the same thing, the same exact thing, but slightly faster calculation. I'm just gonna have to get the squares of x's, and that's it. And oh, okay, I'm gonna have to make a square of all of the sum of the x's. That's not too hard to do. Just single number to make a square of. I have to divide that with the 5, with the number of things I have in the sample. Not necessarily 5, depends on the sample, but this sample 5. And I have to subtract this, and I'm gonna get this denominator. So I have this second formula here, in which I replace that numerator here with this numerator here. They're exactly calculating exactly the same thing. I'm going to show it in a moment. And the rest is the same. Downstairs I have the n minus 1, I have downstairs n minus 1, I have a radical at the end, I have radical at the end there too. So the only difference is what I'm calculating above, what I'm calculating here. So let me show you the calculation. So you can choose either one of them you want. I am actually going to use the formula number 2. It's easier. And then I'm also having this formula number 3, which is basically the formula number 2 with a slight modification. This one, I wrote this one because it's in the textbook. It is in the textbook. So if you multiply up with n, you get n multiply with this term, n multiply with this term, it erases cancels the n, so you get just only this left. And down there you multiply with n, so you got the same thing here. So you can use this formula too. It's in the textbook. But I'm gonna keep on using this formula. It's easiest to me to use. Okay, even though it looks the worst. So now, how I'm gonna use it? Okay, I'm gonna show you the example of using the formula number 1, and then I'm gonna use the formula number 2 as well. Okay, so for the formula number 1, you will need 3 columns of your table. Five data points. So you have x, which is 1, 2, 5, 7, 8. In the formula, you also need to calculate displacement. So you need to calculate the mean. I already did, so that's good. But I also have to subtract every single data point from the mean. 1 minus 4.6 is negative 3.6. What I'm doing here, subtracting x minus x bar, the mean. 2 minus 4.6 is negative 2.6. 5 minus 4.6 is 0.4. 7 minus 4.6 is 2.4. And 8 minus 4.6 is 3.4. Okay, this is not too hard to do. Okay, but now you need to square it also. Because the formula says you need the squares. It says x minus x bar, but you also need to square that. So, okay. Now you have a problem because you have to square all those decimal numbers. 3.6 squared, I don't know that out of my hand. I have to do the calculator thing. I get 12.96. You can see the reason for square. We don't want to get rid of the minus here. 2.6 squared is 6.76. That's good. This one is very easy. 4 times 4 is 16, but you have 2 decimals, so 0.16. 2.4 squared is 5.76, which is nice. And then the bottom you have 3.4, which is going to be, I don't know, let's see, 11.56. Okay, now you need a total. This one says you need to make a total. So the last row is going to be my total. I'm only going to make a total out of these numbers. I don't need anything else. The total of these numbers, okay. I am getting 6 plus 6 plus 6 plus 6 plus 6, 0, 3 carry on. 3 add to 5, 8, 15, 16, 23, 32. 2, 3 to carry on, and now I have 11 and 12. When I go 11 plus 5 is 16, plus 6 is 22, plus 12 is 34, plus 3 I'm carrying on is 37. So I have 37. Okay? So this is my numerator. So you can say, using the formula number 1, okay, this is a piece of a table, right? Again, I was not adding this, so I was just adding this thing here. The calculation says now you have to use this 37.2 divided with 4, n minus 1, n minus 1, pi minus 1, and you end up with the, if you divide 37.2 with 4, you get 9.3, and when you take a radical of 9.3, see, lots of calculation, is approximately 3.05. Approximately 3.05. It has more decimals, so I am not going to, write all of them, but that's approximation. Okay. So I'm going to show you, if you use this formula, it's slightly easier to do that, and that's why the formula is better to use. Because anyway, during the test time, you can just look at your paper where the formulas are, right? So I can't check whether you're using formula or not. So this is easier to use. This here requires only 2 column table. Again, I need the x's and I need the x squares. Okay? The x's are 1, 2, 5, 7, 8. Look how easy this is. Now I need the x squared, which is 1, 4, 25, 49, 64. I'm just making a square, so the numbers in the first column. And again, I need totals. The totals are going to be 23 here. That's easy. I don't know why I'm writing 24. I don't know. 23. Okay. This one is a little more, but you don't really need a calculator. So this is 113. This is 30. 143. That's all that you need, okay? No decimals, no squaring, no negative numbers, right? Easier. Now, in this formula, you're gonna have S is equal radical. What is this? Sum of x squares, 143. Minus sum of x squared, 23 squared. Okay? I know, that's 529. It's not too hard. 23 times 23. 20 times 23 is 460. 3 times 23 is 69. 69 and 460, 529. And then you have to divide with n, which is 5, here. In the formula. Be careful how you use the formula. And down there, you still have to divide with the 4. 5 minus 1. 5 things, 5 minus 1. Degrees of freedom, 4. So, I have a little problem here. So I said, oh, this is 529. I need to divide it with 5. I can do that on a piece of paper, but I'm just going to use a calculator. 529 divided with 5. And my calculator says 105.8. Okay? So instead of writing a whole new row, I'm just going to use I'm just merging everything here. I try to write it in 105.8. Okay? Guess what? This is 37.2. Right? Check it out yourself, right? 43, 100 minus 100. 43 minus 5.8. That's exactly 37.2. And that's what I was promising is going to happen. These are the same calculation, yield the same number. Now, not the same calculation, but they yield the same number. So I have the same thing here. Which basically means that when I proceed this, I'm going to end up with the same thing here at the end, which is going to be 3.05. Okay? So whether you like to use this formula or this formula, I'm going to keep on using this formula. Okay? Again, this thing here the sum of x minus x bar squared, you have to do first x minus x bar for every data point, then you have to square every data point, and then you sum at the end. The sum goes at the end. And this formula, it says sum of x squares, 143. Sum of x is 23, so you get sum of x squared, which is 23 squared. I already said it's 529. So you have 143 minus 529 divided with 5. That's it. And on the top you get the same thing here with a little less calculation. Again, no decimals. I didn't use decimals, didn't subtract anything. I just needed 2 columns also, rather than 3 here. So this is a preferable formula. You can also use this formula. You can use this formula with the same table. Because what you need here is 5 sum of x squares, 143. What you have here is sum of x's, which is 23. Then you have to square it. It's again 529. So you can use this formula as well. Down there you have 5 and 5 minus 1, which is 4. So if you use this formula, it's basically the same table. Okay? So I think this formula is pretty good to use. This one is in the textbook. You can use this one too. You can also use this one, but you're going to have a little more calculation to do. Okay, that's the story about calculating sample standard deviation. What we got is 3.05. On the way, as you can notice here, before I took a radical, I got 9.3. 9.3. Without radical, this is called variance. So you have here variance. This is basically the square of a standard deviation, because this is just simply, the whole calculation is exactly the same. The only difference is that you don't have a radical. So if you are taking a square root of variance, and you know what the variance is, 9.3, then you get 3.08, 3.05, which is the sample standard deviation. That's the story. Now, you can do the same thing with the population, but there is a slight difference when you do that with the population. Okay, so why would you want to do it with the population? Well, if this is a population, then you're going to be calculating population standard deviation and population variance. The relation between the variance and the standard deviation is always the same. The variance is a square of a standard deviation. The standard deviation is a square root, radical of variance. So that holds. But there is a difference in the calculation when you are doing the population standard deviation or a variance, and when you are doing sample standard deviation or sample variance. Okay, let me point this out, what the difference is. So the story about the calculation is that you need to know ahead of time whether you are talking about the population or you're talking about the sample. So for a moment, let's pretend that this is our population in the game here. Because of course, when you have some 5 things, it's very unlikely to be a population, but it could be, right? You would not know. Unless somebody tells you. They didn't tell you anything about what is this 1, 2, 5, 7, and 8. Okay. Looks like I'm just at the end of this map of mine. All right. Okay. This is the different formula we're going to use for the population. So, if you look at this, first difference is going to be that I'm going to use the Greek sigma, Greek S, which is the Greek character. Whenever we refer to population, we use Greek characters for the population. So the Latin characters for the samples, Greek characters for the population. You will have a radical as well. You will have this summation of the sample points minus the mean of the sample hey, I just said this is a population, so it's going to be a mean of the population, which we label differently. But it's calculated the same way. It's the average, arithmetic average of everything that is in the population. It's just a different label. You still have a square. Okay? So I'm referring to this thing you see here. Right here. I almost have it. Now the trick. When we're talking about the sample standard deviation, down there in denominator we have n-1, which is degrees of freedom. 5 things, 4 degrees of freedom. Or when you're doing a population, the population has no freedom. And you're going to be dividing with the size of the population, which in this case is 5. We also use the notation for the size of the population, we use uppercase n, as opposed to lowercase n for the size of the sample. That's just a cosmetic difference, but this is a real difference here. n minus 1. In here 5, in here 4. So that's a big difference, okay? Now you have the same story here. If I write a table, I would write the same table I was writing for this formula, which means on the top I would end up with the top is exactly the same except for a label. Here the label is me, Greek me, micron. Here is the mean of the sample, but it's still 4.6. So I just changed the label of the average. For the population average, population mean is labeled with Greek m. But I still get 37.2. So I'm not going to write the whole table to get to the same thing. I know already this is going to be 37.2, just like here. The only difference is now I'm going to divide with 5. Okay, rather than 4. When I was calculating sample standard deviation, I had 4, which means I'm going to get smaller number because I'm dividing with a bigger number. Okay? The end result of the story here is that population standard deviation is going to be smaller than the sample standard deviation of the same set of numbers. But this cannot be sample and a population at the same time. It's one of the two. Okay? And population takes over. If you're talking about population, you say population. You can say, oh, this is the sample is equal to the population. No, that's a population. Okay? So we have the 37.2 divided with 5. I need to do that. I get 7.44. And again, I'm going to have to take approximation here. I'm doing the radical and get 2.73 approximately. Okay, different than what we were calculating for this guy, for this particular sample. When we were doing this particular sample, we had 3.05, and that was also approximation, 3.05. I just squeezed that in the corner because I already erased that. But this one is smaller. Population standard deviation of this sample is smaller than the sample standard deviation of the sample. Meaning that I'm really thinking about that this is a population, so it's a different number. This 7.4 before radical is a population variance. Again, the same as for the sample. Population variance is a square of population standard deviation. Sample variance is a square of sample standard deviation. So that relation stays. So the variance is always the square of the standard deviation, whether it's population or sample. That is no change. Okay, so notice this change of average. Dividing with 5 as opposed to dividing with 4. Right? You have to be aware of that. So, starting with the calculation, you need to know which statistical parameter you're calculating. Is it a sample, which is statistic, or is it the population, in which case it's a parameter? Unchangeable, right? Population is unique. There are not 2 populations, 3 populations. It's 1 population. A sample could be on this sample, and that sample, and this sample. So We call it, for population statistics, we call parameters, right? Okay, so let's go back to the lecture. All right. Okay. I should enlarge that, but I'm not gonna play with that now. Okay. So there's also, I'm really not going into that, but there's an also calculation you can do, the simpler calculation when you're doing population variance, meaning that this expression here, before you take a radical, could be calculated simpler by using the two-column table, in which you will just need the sum of x squares and sum of x, as you can see here. So this is the average of the x squares. You sum all of the x squares and divide with 5, so it's the average of the x squares. And this is here the average of the x's squared. I could do that too. Like, I have that old table that I had. I still remember what I had, so I could recover that. So I'm saying that this 7.44 you could get by following this easier formula. So this is the formula that is an easier formula to calculate the population variance. Okay, so that I am not going to really use that much, because I will rarely calculate the population variance, but you could calculate it. So the population variance, so this is a square, the 7.44 of the sample, excuse me, population standard deviation, can be calculated by the mean of the squares minus the square of the mean. Well, it's kind of easy to remember. Mean of the square minus square of the mean. So that's the formula here in the lecture. Okay? So I kind of remember this. This was 143 divided with 5. This was 23 divided with 5. I need to square this, and I need to subtract it. And I'm leaving that to you to convince yourself that this is actually 7.44. Well, you know, let's not be lazy. So 143 divided with 5 is 28.6. (23 divided with 5 is 4.6. So that's this guy actually. Square that. My calculus says 21.16. And I'm not going any further. Yeah, this is 7.44. Okay, so again, you have this formula to calculate this population variance that is a little bit easier than what I was doing moments ago. So this calculate population variance, and of course, if you have a variance, the standard deviation is just as radical. So you just make a square root of that. Okay. So let me show you a few more calculations. But okay, I need to mention something else. There's another measure of dispersion. It's called coefficient of variation. Let me give you an idea of what that is. So sometimes you have a situation in which the sample have the data has the same jumps away from the central value, but in common sense approach, it's not the same dispersion. And what am I talking about? You know, how can that possibly be? You have the same jump away from the mean, but it's not dispersed the same. Okay. Now I'm going to give you simple idea on that. Okay, so you could have a sample like this, 1, 2, 3, and you could also have the sample like this, 101, 102, and 103. Okay, so 2 different samples. Okay, let me think about that a little bit, what I mean by these numbers. Okay, what can I see on the first 3 numbers? Price of coffee. So you go for a cup of coffee. One place $1, another place $2, another place $3. Is it a big difference? Yeah. I think most of the people will agree. What's the big difference? I don't want to pay $3 if I can drink coffee for $1. Okay, so this is not the same dispersion. Excuse me, it's a large dispersion. Okay? It's a big difference in my view. The second sample, what could that be? I don't know, I can hardly find out something $101. But let's think like that. I have, neighbors. I'm kind of an elderly guy, so when the snow comes, somebody needs to clean my driveway for me. I have a double driveway, so you need to, put up, if it's a deep snow, you need to put up the snow blower and, do some work for an hour. Okay, I can pay somebody like a 16-year-old guy. I can pay him $101. There's another guy asking $102. There's a third guy asking $103. Is that a big difference? Not really. So dispersion of this sample, 101, 102, 103, is not much of a difference. To me, right? I might be more concerned in this case, who's going to do better job. So if I know that somebody's a little more serious, I'm going to probably hire him, even if it's $1 more. It's not a big deal. But here's the trick what you have here. If you calculate the sample standard deviation, the first sample is going to be 1. The sample standard deviation, use a calculation by any of the formula that I mentioned, 1, 2, 3, choose whichever you want. You're going to get 1. If you calculate the second sample standard deviation, it's also going to give you the sample standard deviation of 1. That's interesting. Not a big surprise though, okay? Because you have the average, which is 2, you have the average, which is 1 or 2. And this thing goes 1 away from the mean, this thing goes 1 away from the mean, and that's the whole story. In here, the same story. This guy goes 1 away from the mean, this guy goes 1 away from the mean. In other words, the standard deviation doesn't take into account how big the numbers are. But we do when we think about it, the price of coffee versus the price of, driveway. If somebody gives me a price of snow blowing the driveway, I know that the 101 and 102 is not much of a difference, not to me. But in terms of a coffee, 1 to 2, there is a difference. It's double, right? So, and standard deviations won't show you that. That's the point. So we need another measure that can show you that. And that other measure would be the coefficient of variation. So the coefficient of variation is this formula we use here. For the sample and for the population is done. For the sample and for the population is done the same way. You will have to divide the standard deviation with the mean. Standard deviation of the population, mean of the population. Standard deviation of the sample, mean of the sample. What's this 100 here? Well, nothing then, simply once you finish that division, you will express that as a percentage. So you kind of have to multiply 100 to get a percentage, okay? That's the whole story. So you are going to get the percentage. So coefficient of variation is referred to by a percentage, okay? So I already told you that sample standard deviation here is 1. Well, the mean is obviously 2, right? 1 plus 2 plus 3 is 6 divided by 3 is 2. So the coefficient of variation here, if you divide 1 with 2, sample standard deviation with the mean. Mean is 2. Sample standard deviation is 1. I didn't really prove that, but I'm going to leave it to you to entertain that calculation. So if you divide this one with this one, you get 0.5, which is when you express as a percentage, you multiply 100, you get 50%. Okay? How about the second sample? So I already said, I think I did, I shouldn't be writing the mean of the population because I'm talking about a sample, right? I'm going to lose my mind over this erasing it just doesn't work really all that great. All right, but I have 102. Okay, and the sample standard deviation is 1 mean of the sample. So the coefficient of variation of the second sample is 1 divided by 102. I don't know, that's kind of a small number, but 1 out of 102, 1 out of 100 is 1%, right? So it's going to be something like a 1%, even a little less than 1%. So I'm going to pretend like it's 1%. And you can calculate that, 0.98 or something like that. I'm going to just use 1%. So look at that. The one on the top has a coefficient of variation 50 times bigger than one on the bottom. Okay? So which means the coefficient of variation is a comparative measure. You can compare two samples that have nothing in common. What does coffee got in common with the snow blowing or driving? Nothing. That's snow blowing or driving is a heck of a lot more work and more expensive, of course, than cooking a cup of coffee. So they have nothing in common other than a price, and both are in dollars, but they're completely different things. But I can compare, and I can say now that the first sample has a 50 times more variation than the second sample. Not by sample standard deviation, because it's the same in the first and the second sample, 1. But by using coefficient of variation. That is important. Okay, so this is a comparative measure. We're not going to use it often, but when we need to compare the variation of two different samples that might not have anything in common, we're going to use that. Okay, let me show you 2 more examples in the lecture that is actually using that. So the first example here in the lecture is the this would be a sample of 7 computer companies, the random sample of 7 computer companies, the profit per employee in thousands. $29,000, $24,500, $31,000, $29,800, $21,800, $27,700, $19,100 in thousand. Annual profit per employee. What's that? You have a company, you have 10 employees. As much as you make a profit at the end of the year, divide with 10, which is the number of employees you have, and that will be the profit per employee that you have. This is after you subtract the cost and everything, and salaries and wages and the healthcare, whatnot you're paying for your operation. So it looks like these computer businesses are doing all great because they all have positive profit per employee, right? If you have negative, that's a problem. Then you're losing money. If you have 0, that means you're just breaking even. You're not making any profit. But if you have money like that, depending how many employees you have, it looks like you're making a lot of money. I mean, this third company is making $31,000 per employee annually. So you have 1,000 employees, that's 31 millions. Now, what's the standard deviation of the sample? Well, first of all, range. Range is 31 is the biggest number. The smallest number is 90.1. And you subtract that, it's 11.9, $11,900. Okay. And then I'm doing calculation for standard deviation. So I would, of course, easily calculate the maybe not so easily, but with help of a calculator I can calculate mean of the sample. So I'm itemizing all of those guys. I'm adding them. I get 182.9. I have to divide it with 7, and I'm ending up with approximately $26,130. So again, this is in thousands of dollars. Now I'm going to do sample standard deviation. I'm going to use this formula on the board, which is the same as the number 1, number 2 is the same thing. The only difference is which numerator you're going to calculate. I'm going to calculate this numerator. It's easier to calculate than one on the top, but they're the same thing. And in this particular sample, we ended up with 37.2. Whether we calculate this or that numerator over there, the same thing. Okay, so that's what I'm going to need. I'm going to need the squares. So the square of 29 is 841. The square of 24.5 is 600.25. The square of 31 is 961. And when you go, all of those are squares, the guys in the first column, or you can ask what is this 1, 2, 3, 4, but it's just itemizing them, you know. Sometimes you might have a name, sometimes you have just number 1, number 2, and so on. Okay, you actually don't need this column at all. I just put it out because I don't want to have this total, the sigma, the sum, kind of hanging around. So let's add all these guys to get 4,897.63. That's the, I should say, square dollars, whatever that. It doesn't make much sense, but that's what it is. And now I'm using this. I'm calculating this numerator. This numerator that I was writing either there or there, either one you want. I'm actually going to calculate this one here. So I am getting the sum of x squares minus sum of x squared over n. So sum of x squares, and I have that here, 4897.63. Sum of x's, that's 182.9. Square that, divide with 7, and then finally subtract both of them. So blah blah blah, here it is, 118.71. That's just a numerator. Now I need this numerator, which is, so that's the numerator here or here. What do I need to do? I need to divide with n minus 1, which is the, I have 7 companies, so that will be 7 minus 1, 6. And then that's a variance, and then I need to take a radical to get standard deviation. So I did that, 118.71 divided with 6, and I take the radical, and I got 4.45. That's a sample standard deviation. Okay? Now, this is in thousands, so thousands of dollars. So the average jump away from the central value, the average of those profits per employees of this computer company is, on average, they go back and forth about $4,450. Okay? Now, in terms of coefficient of variation. Now, what will be coefficient of variation? You need to divide here, which is the sample standard deviation, with the mean, 26.13, which is we calculated right here, right? So when you divide this and this, you end up with 0.17, or now multiply it with 100 to get percentage, you get 17%. I don't really multiply, it's just the same thing. 17%. 0.17 and 17% is the same thing, so you don't really need to multiply. This multiplication is just for the elementary school students. So 0.17 is 17%. The variation of the sample is 17%. That's not big variation of the sample. The sample is not very, there are no big variation here. It will be more interesting if you have some company that makes a really lot of money and some other company that loses money, then it would be bigger variation. But these guys are all making money, and there's only one that makes less than 20,000 per employee, and there's only one that makes more than 30,000. So they're all in 20s. So kind of you can see that there is no big variation. Okay, so 17% variation is coefficient of variation is not big. Okay, let's see the one sample that has a lot more variation. This is the percentage of the Canada goose nests that are successful. Okay, Canada goose is the species that flies from north to south in fall and from south to north in spring, nests in northern part of the United States and southern part of Canada, and the nest is considered to be successful if you have at least one gosling coming out and out of the nest. If nobody comes out, if the all eggs are broken, or the elders get killed somehow on the way, then you get nothing. Then it's not successful. So what we have here is a big difference from region to region. On one region we have 23.9% nest successful. That's less than 1/4. That's really bad. There's probably lots of people there. And one region you have 52.5% nests are successful. That's good. Then 60% of the nests successful, 68.5%, 78.6%, that's more than 3/4, that's good. 71%, and on you go. 17.8%, that's really bad. 59%, 52%, okay? We want them to be successful, right? We want those birds around. Even though they put a lot of droppings around our college, when you see them, you can see them twice a year. They come around, they always congregate around our college on lawns and before they go somewhere else, right? They need to take a break, of course, they're flying long flights. Okay, So you have the range is 60.8, and you subtract 78.6 and 17.8, which is the smallest number, you got 60.8. Okay. Now, in the table for calculation, I said already I will need access. I just itemize all of the guys here. Well, I put 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't need that, but I itemize them here, and then I made the squares here, right? So which means that this 5041 is a square of 71, and the same thing in every row. And then I need the sum of the x's. I get 483.3, and I need the sum of the x squared. So you see I have here 29,340.51. Okay, this is all calculator business. You can do that. By the way, I'm going to show you somewhere down the road how to do it using calculator. TI to TI-84 I'm talking about, right? Of course, you can do that piece by piece with any calculator. So the mean nest success in the northern America, northern part of North America, so northern part of North America is 53.7%, because I just simply added all of those guys. 483.3 divided with 9, we got 53.5%. More than half of the nests are successful. So I guess they are still okay. If we are not killing them, right? Some people shoot at them for sport. I hope it's forbidden, I don't know. And so now we want to calculate the standard deviation. So the standard deviation calculation is, again, I'm going to use this formula. Numerator is the key. I calculate numerator. The same numerator is there. Although they look different, the calculations are different, but the number at the end is the same. So I'm going to use this one here. And so that's the sum of the x squares here. Sum of the x squared divided with n. That's exactly what it says. Sum of the x squares minus sum of the x squared divided with n. Okay? So sum of the x squares, I got 29,340.51. Here you go. Sum of the x is 483.3. I need to square that. I need to divide it with n, which is 9. So, after all that is done, I am not going to do that piece by piece. You check it out. I got 3387.3, 3387.3. Okay, that's just a numerator. So the standard deviation, according to the first formula over there, I need to divide that numerator with n minus 1. This sample has 9 things in it, so n minus 1 is 8. Degrees of freedom of this sample is 9 minus 1, which is 8. And then I have to take a radical. So when I do that, so I got 3387.3, I need to divide with 8, and I take a radical, I got 20.58. Perfect. This is a sample standard deviation of this Canada geese nesting sample. Coefficient of variation, again, I need to divide the sample standard deviation, 20.58, with the mean, 53.7. When I divide these two numbers, I get 0.38, and the coefficient of variation, again, you multiply with 100 and read this as a percentage. And I'm getting here 38%. 38%. Okay? The computer companies, 17%. The Canada geese nesting, 38%. More than double. I have already seen that. That's why I'm showing you this example, because I can see that there's not that much diversity or dispersion in the computer company business, but there's quite a bit of dispersion in the nesting of Canada geese. So no surprise here. Coefficient of variation told me I can compare the two samples. They have nothing in common. The first one is in thousands of dollars. The second one is a percentage of the nesting success. There's nothing in common here. But I can compare the dispersion, because dispersion is about numbers. And the second sample has more than twice the dispersion of the first sample. The first sample has a 17% coefficient of variation. The second one has 38% variation, okay, which is a bigger variation, much bigger. Okay, food for thought. The last item in this lecture is about a bunch of samples that I'm leaving to you to calculate. Of course, you're going to have a homework. Measure the dispersions in the homework. That's Lots of calculation for that homework, but so what I'm saying here, I already pointed out something before. 1, 2, 3, 4, 5, and 11, 12, 13, 14, and 15 will have the same standard deviation. The average is the central value, 13, 3, and the rest of the guys are going 1 left, 2 left, 1 right, 2 right. The same thing here, 1 left, 2 left, 1 right, 2 right. Okay, so the standard deviation turn out to be the same, but of course the mean are different. The first one has a mean of 3, the second one has a mean of 13. So when you divide, the coefficient of variation is going to be significantly bigger in the first one than in the second one. We're talking about the same thing with that coffee driveway snow blowing case, right? Now in here, I'm talking about a sample that has 1, 1, 1, 1, 5, and a sample that has 1, 5, 5, 5, 5. Both of them have the same standard deviation. No surprise there. The central value here is different. This one has a central value, I don't know, 1.8. This one has a central value of 4.2, something like that. Yeah, it's written down there, 4.2, 1.8. Just didn't notice. Kind of remembering that. Now this is 1.79, 1.79 is the same standard deviation. But you can see that this is just basically one of them is a mirror of the other one, mirror image, in terms of what the central value is. And the coefficient of variation, of course, is vastly different. The reason for that is very simple, because the coefficient of variation takes into account the mean. The mean of the sample is much smaller. The mean of this sample is much bigger. 4.2 is much bigger than 1.8. So that's why the coefficient of variation comes up differently. And this sample also, just I added another one, 1, 1, 3, 5, 5. The mean is 3 again, but it's a different sample than this first one. 1, 2, 3, 4, 5. And this one is 1, 1, 3, 5, 5. Slightly different, right? You have 3 as a central value, which is a mean again. But now the other things are further away. 1, 1 as opposed to 1, 2. 2 is closer to 3 than another one here. And so you get more of a standard deviation. Instead of 1.58 as the first sample, you get now 2. Okay, you can calculate it yourself to convince yourself. And then of course you got the bigger dispersion. Dispersion now is the coefficient of variation, right? Coefficient of variation is bigger. The first one is 53%, this one is 67%. Because of some guys are going, like this one here goes further away from the mean than in the first sample, which is 2 here. This 5 goes further away from 3 than this 4 goes. So it has to be a little more coefficient of variation. So you might want to think about this a little more, take a look at that, what that tells you. And I'm done with this lecture. You of course have to do homework, and again you have 3 formulas you can use. I keep on using this number 1 and number 2. Actually number 2 is basically the same as number 1, except for the numerator here, numerator there. It makes different calculation. This one is easier to calculate. You have two columns of the table. And the number 3, you can use the same table as the number 2, and this is kind of a little different calculation, but if you use this, of course you're going to come up with the same number at the end. This is for sample standard deviation, all 3 of them, not a population standard deviation. Okay, so sample standard deviation is the same whether you use number 1, number 2, number 3. This one and this one uses the same table. This one and this one has the same numerator. That's the difference. This one is in the textbook. It's a nice formula to use. It looks simpler than this one and uses the same table. Is it kind of like a nicer formula than this one? I don't know, maybe not. And uses the same calculation, the same table. It's equally difficult or easy depending what you look at, what your skill is, right? Okay, so that would be it. Now I'm gonna keep this stream for a while on the YouTube, so I'm expecting you guys to do this watching when you have a time, maybe even repeat it. If you don't understand something, you can go back and think about what I was talking about. And of course the reading of a lecture, because I really didn't do manual calculation on all the stuff that is in example 1 and 2, I'm leaving that to you to check it out. I mean, I'm quite sure the numbers are okay, but you should do the calculation and convince yourself. All right, so see you next time when we have the lecture number 6 in the class.